Okay, recording has started, so good afternoon, everyone. If you're watching from home, I was just talking about the exam, which the average was 33 and a half out of 50. So if you got somewhere close to 33 and a half out of 50, you can view that as more or less average. So probably in the scope of the course, if a curve is applied, then it would most likely mean that if you got a score near to the average, you're probably sitting around the C mark. If you did somewhat better, you're probably up into the B's or the A's. So that's how I would think about the exam. Now, I do want to remind everyone that the exams and the final exam make up something like 45 or 50% of your grade, and then the rest of your grade comes from the homework and the quizzes. So homework and quizzes are a great way for you to pad your grade for the class. So, you get 6 attempts on every homework question. So in my view, I think it's reasonable to shoot for 100% on every homework, because you can go through it once, just try every problem, see if you get them right. If you don't get them right, go back, check the notes, try for your second attempt. You still got 4 attempts after that. You can come to office hours, you can go to Daria and the SI, you can go to the Math Tutoring Center, lots of options for you. I think you can get a lot of help, and it's a good goal to shoot for, to get hundreds on all the homeworks to pad your grade. Any questions about the exam that we should discuss immediately? Okay, like I said, there's a solution on Blackboard, so take a look at that. If you still have questions on any of the problems after viewing that, then please come and talk with me during office hours. I posted a new homework on sections 4.3 and 4.4, so we're doing 4.4 today, and that homework will be due 1 week from today, April 7th. It's 20 questions long, so it's a little bit longer than some of our other homeworks, so you might want to start early on that one. And on the same day, April 7th, we're going to have quiz 6. And I suppose I should tell you which sections that's going to cover. That'll be on 4.3, 4.4, and 5.1, probably, because that'll be what we do on Monday. Okay, so that'll be quiz 6. And then, not on Monday, on Tuesday. And then on Tuesday, I'll also post a new homework for Section 5 if you want to practice some Section 5.1 problems before the quiz. All right, so that's all I have to announce administrative-wise. Does anybody have any comments or questions or concerns about anything of that nature before we start in on new material? Okay, if not, then let's get started. So today we're going to talk about section 4.4. Oh, let me give some context for where we are at in the class. So, okay, we are at the end of chapter 4 right now. So in sections 4.1 and 4.2, which we studied for the exam, we learned about local mins and local maxes of functions. And then in section 4.3, which was not on the exam, but we did cover in the lecture before the exam review, that was on global mins and global maxes. So I'll review a little bit about global mins and global maxes, and then we'll get into section 4.4, which covers some applications of min-max theory to cost, revenue, and profit, and also some optimization problems are in there as well. And then starting next week, we will move on to integration theory. So everything we've done up to now has been sort of, we learned what a derivative is, and we learned how to use derivatives in applications. Next chapter, we're going to learn about what are integrals, how do we do them. We're going to learn about the so-called fundamental theorem of calculus, and then we're going to learn some special integration techniques and some applications of integration during that chapter and chapter 6 as well. So that'll be basically the last month of our class is spent on that. So Before we go into 4.4, I want to look back at section 4.3 and remind us what we were doing with the global max and the global min theory. So the goal was, if we have a function and we define the bounds on which we are going to care about this function, so we say, I'm only going to care about this function between a and b. And if I limit the scope of my perspective to just in this small region, I want to look for what I call the global max and the global min. Now, local max is a point which is higher than its neighbors, okay? So I can find some small neighborhood of that point such that it's the highest point in that neighborhood, okay? And the global max is going to be the point on the entire world, okay? Being our scope from all the way from A to B, and it's the highest point in the entire interval. So that's the difference between a global max and a local max. It's like the difference between a world champion and a state champion, right? If you're the best in your state, you may not necessarily be the best in the world. Okay, so that was global min and global max, and we had a theory for how we find them. And that was as follows. I've written it out here, so I don't expect you to write this out as we're talking about it, but please do take a look at the notes after I upload them onto Blackboard to see this if you want. So what is our process for searching for a global max and a global min? So this is just a recap. The first step is to find all of the critical points of the function, which are between a and b. Of course, if I have a critical point somewhere outside of my interval, I don't really care about that point because it's not going to be a global max or a global min for my interval. I'm only interested in what's going on in here. So if there's a critical point elsewhere, I'm not going to worry about it. So what I need to find are, where are all the critical points which are inside of my interval? So that's the first thing I do, is I find the critical points which are between A and B. And step 2 is I'm going to make a table. And what do I put in the table? I put in all of the critical points which are between A and B, and also A and also B. Okay, and these, we decided in lecture last time that these locations here are the only places where it is possible for me to find a local max, or I'm sorry, not a local max, a global max or a global min, okay? So what do? I just find out what is the value of the function at all those points, and then I look for which number is biggest, right? Whichever number is biggest, that's going to be the tallest point of the function in between A and B. It has to happen either at the endpoints or at one of the critical points. So I look for the biggest number, and I say, aha, that's my global max. I look for the smallest number, and I say, aha, that is my global minimum. Okay, before we do an example, are there any questions on this sort of algorithm that we use? So let me pose a question for the class. What's the big difference between looking for a global max versus looking for a local max? Shania?
Global maxes are just in that specific small area that is the highest, whereas the global max is the highest area within the whole function.
Yes, that is exactly the difference between a global max and a local max. Now, if I'm going to try to find them, right, I'm looking at this process here, where I'm gonna look at the critical points and the boundary points. How is that different from when I look for local maxes and local mins? There's one crucial difference here. Does a global max always occur at a critical point? No, where else can I find a global max? At the boundary. So the crucial difference between looking for global maxes versus local maxes is I also need to check the A and the B, the edges of my boundary. Okay, that is a crucial difference. All right. Okay, so let's do an example here. So you'll probably recognize this function from the exam. So we want to find the global min and global max of this function, f of x equals x cubed over 3 minus 9 halves x squared plus 14x minus 1 on the interval from 3 to 10. Okay. So the first step, based on my algorithm, it says what I need to do first is find the critical points, which are between a and b. So first of all, I've got my a value is going to be 3, right? And my b is going to be 10 in this circumstance. So I need to find the critical points of this function, which are bigger than 3 and smaller than 10. So let's go ahead and do that. The way we're going to do that is just by taking this derivative, f prime of x. Now, how do I take this derivative? First, I'm going to rewrite this in a little bit of a way. There's two different ways in which I could take this derivative. The first way is to say, okay, I'm going to view f of x as 1/3. Okay, dividing by something by 3 is the same as multiplying by 1/3, right? So 1/3 times x cubed, and then we've got minus 9 halves times x squared plus 14x minus 1. Now, I just take the derivatives piece by piece. So this is, I have a number times the function x cubed. The way I do that derivative is the number is going to just hang out, right? So I get the 1/3 just floats. And now what I need to do is multiply that times the derivative of x cubed, okay, which is 3x squared. So that's how I got that derivative. Now, I can hear the murmurs of students who might say, well, how do I know I'm supposed to rewrite x cubed over 3 as 1/3 times x and use the constant rule? Well, fine. You don't have to use the constant rule here. So if you didn't notice that you can rewrite this in this way, then of course you can use the quotient rule. How would I do the derivative of x cubed over 3 using the quotient rule? I would take x cubed as my f, and I'd take 3 as my g. And then I would use the quotient rule, which says I should do gf prime minus fg prime all over g squared. Well, if I do that, my f is x cubed, so g times f prime is going to be 3 times 3x squared, and I subtract from that f times g prime. Well, g is a constant, so its derivative is 0. So I get x cubed times 0. And then I divide all of that by 3 squared, which is 9. So what do I get? I get 9x squared over 9, which is just x squared, which is the same thing that I got using this number rule, right? Okay, so two different ways we can handle taking a derivative like that. And if you get stuck on something like that and you're not sure what to do, then just, at the worst case scenario, rely on your derivative rules. I have something divided by something. Quotient rule will get me there. It's not the most elegant way to do it, but that's a reasonable option. Any questions on how I did that part, first and foremost? Okay, that was just something I wanted to clear up because I noticed a lot of mistakes on the exam at that point. Okay, so next part is just going to be 9 halves times 2x, right? Minus 9 halves times 2x, which, of course, if I simplify, becomes just 9x. And now I have plus 14 and minus 0. So this becomes plus 14. Okay, so this is f prime of x. And now I need to find out when is this equal to 0. So I factor x minus 7, x minus 2. I need two numbers which I add them together and I get negative 9. I multiply them together, I get positive 14. Equals 0. This tells me that x is equal to 7 or x is equal to 2. So I found the critical points. Now I'm going to move on to step 2. I'm going to make a table with all the critical points and the boundary. So here comes my table. X, f of x. What numbers need to go in here with my x? 3, 7, and 10. Why not 2? Yeah, x equals 2 is a critical point of this function, but it is not in between 3 and 10. So it is outside of my realm, my scope of my search. Okay, now on the right-hand side, all I'm going to do is plug these numbers into the function. So 3 cubed over 3, that's, what is that, 9? And then minus 81 halves, right? Wait, 9 times 9, yeah. And then plus 14 times 3, whatever that is. Okay, so, you know, we're going to get some numbers here. Okay, fine, we'll do the whole thing. We'll plug in 7. I think 7 cubed is 243, is that right? No, yeah, it is right. 243. Sorry? Is it 343? Okay, let's bust out the calculator and do this properly. Yeah, you're right, it's 343, thanks. Okay, so we've got We've got 9 minus 40.5 plus 14 minus 1. So that's 9 minus 40.5 plus 14 minus 1. 9 minus 40.5 plus 14 minus 1. Negative 18.5 at 3. That's what I'm getting. Okay, then I've got 7. I need to do 343 minus 9 halves times 49 plus 14 times 7 minus 1. 9 times 49, divide by 2. This is 220.5. This is 98. So what do I do? All I'm doing here is I'm just plugging these numbers in, right? And I'm just going to search for the biggest or the smallest number based on that. I get 219.5 here. Okay, now for 10. 10 should be easy. I just get 1/3 times 1,000 minus 9 halves times 100 plus 140 minus 1. So this one is 450 and this one is 333.33. So 333.33 minus 450 plus 140 minus 1. 22.33. Hang on. Did something go wrong?
So you plug in 4 or 3 into 14x for 3.
Thank you. This should have been 14 times 3. So we add 28. So this should be okay. This is taking way too long. Yeah, 9.5. Okay, in any case, assuming that I did this rote calculation correctly, then here's what we do from here. We have our table with the one critical point which happens to be between our boundaries, and then we have our boundary points, right? And if we want to know what is the largest number in here. Okay, I'm sorry, this is bothering me so much. 343 minus 220.5 plus 98 minus 1. There we go. That's what I did wrong. Something went horribly wrong there. And this is negative 90.5. Okay, so all I want to do is look for whichever number is biggest, right? Well, I've got 9.5, negative 90.5, and I have 22.33. So this is telling me that I have a global max of 22.33, and it happens at x equals to 10. I also have a global min. Well, how do I find the global min? I put the boundary points, the critical points, which are relevant in this table, and I look for the smallest number, which is negative 90. And that occurs when x is equal to 7. Okay, now this is consistent with my understanding of this function. So, again, the process is we find the critical points between A and B, we make a table with those critical points and also A and B, and we look for the biggest number. That's how we look for global mins and global maxes. Any questions on this example? Okay, then we're going to do a little bit of group work today. So go ahead and form yourselves into groups. We're going to do one example of a global min-max search, and then we are going to move on to section 4.4. So let's get formed into groups, and we're going to work on the following problem. Let's get formed into groups first, and then I'll say something quickly about this problem. Okay, so let me say something really quickly about this problem before we begin. Okay, so we have a quantity of a drug in a bloodstream, T hours after the tablet is swallowed, okay, and is given in milligrams by this quantity function. And we need to find when is the maximum quantity of the drug in the bloodstream. Now, you can imagine that after we swallow it, okay, then the drug is going to enter our bloodstream, right? So it's probably going to increase in our bloodstream initially. And then at a certain point, we will have absorbed all of the drug and our liver will start to, right, decompose that substance, right? So this is the kind of function we're thinking about as we're moving forward. And we're trying to find the maximum, right? Now what we're trying to find here is a global maximum. Now, if we want to find a global maximum, we need our A and our B, right? Our boundary points for which we are going to start our search and end our search. What's a natural place to start our search in terms of time? T equals to 0, right? So we should search maybe from T starting at 0, okay, and then up to, okay, let's say, why don't we say 24 hours is how long it's going to take for the drug to completely dissipate, right? Based on this function, it's actually never going to dissipate, right? Because that number inside is never going to actually reach 0, right? So that's just something to think about. But again, our goal here is we want to find the global max. I've written out already the derivative for you. So what do we need to do? We need to find those critical points, which are in between 0 and 24, and we got to make our table, right? And plug in. All right, we feel like we got a good idea of where to go from here? All right, go ahead and work in groups. I'll float around. If you have any questions, please just raise your hand. means that one of the two numbers is 0. And this number is never 0, right? So we need to solve this equation.
Yeah.
2e
Well,
minus
yeah, so we're trying to
minus
do
1
two separate, so
equals
you just say 2 would be negative.
Yeah.
So how do we figure out, how do we solve this equation and set this equal to 0? But how do we get t by itself to the next one? Take it down.
And 2 negative 2 is the same as 1 over the 2 over e.
Well, yes, but this is the derivative of this function, right? So the reason we want to check where is the 0 is if we check where is the derivative of 0, that will tell us where the critical points are. So we need to find the value of t such that if I plug it into this function, if I plug it into that number, but negative, and I subtract 1 from it, I get 0. So maybe a good way to start would be to go to the 1 over t. Let's start with that. 2 to the minus 2 equals 1. Right? Right. Well, we'll work on that. So let's do 2 to the minus t equals 2 over 1. Question. You know how I can get this?
And then we have 2 over e.
So that you can find like what.
Yeah, you can find the t for sure. Yeah, you can find it. And now how do I get this t out of the picture?
Based on this point, I think
How to get the unknown.
Yeah, that's how. But I didn't prefer
What's that other function that undoes? On both sides.
I think that's what we do, and then.
Did you find the card? I know we have to have it.
That's the thing, that's what I'm thinking about. I think we have to use,
The negative on this side, right? So whether we do this one pass, right? Yeah, that is.
one of the rules that says that you have.
Okay, we on the right track.
That's raised to a crystal. You can, take the logarithm of that function.
What's going on? Okay, so we got
I
two.
don't know if that's right.
We got an unknown, which is in the exponent, right? That's right, logs, right? So maybe we should try taking logs, but maybe I think first we might want to get rid of that 2, right? Because if we get rid of the 2 on that side, we'll just have e to that thing, right? And if we then take a natural log, what's going to happen? If I take the natural log on the left side, it's going to get rid of the e, right? Alright, let's go over here. Okay, so we have two things being multiplied together, right? 20u minus t, and then this other number. And I multiply them together and I get 0. If I multiply two numbers together and I get 0, then what must be true about at least one of those numbers? It has to be 0, right? But this one's never 0, right? So we need to ask ourselves, when is this one going to be 0, right? So let's set that equal to 0 first. Let's start with just 2e to the minus t equals, or minus 1 equals 0, right?
So that's our only curve point. So then you put the charge, and then you calculate
So, yeah, I would maybe start with the one on the right hand
all of
side.
the ones that you have.
The factored form. Right? So, if we have an equation like this, you know how we can get t by itself. Well, right now, t's kind of bunched up in a lot of stuff. First of all, it's in a power, right? And it's also being multiplied by something. It's also being subtracted by something. So let's just handle it like 1 by 1. we first like move 1 over, right? And just start moving things away from the t, right? So let's start with just 2e to the minus t equals 1. Okay, we've got something like that. Then we can take it a step further and get rid of the 2, right? So we have, yeah, just divide by 2 on both sides. We got e to the minus t equals 1/2.
Alright, now how do I get that to
Right, so now it's stuck up in the exponent. Is there a tool that we learned that helps us to move things outside of the exponent? That's it, natural log, right? What happens if I take the natural log on the left side? We just are left with negative t, right? Okay, we on the right track now?
So, wait, Sarah, can you repeat the first step again? So you just divided by 20?
So I started with this equation. So this was factored out. So I have this thing multiplied by this thing, and I get 0. If I take this thing, which is not ever 0, and I multiply it times something else, and I get 0, then this had to have been 0. So I started with that equation, which is just, I started with the equation 2e to the minus t minus 1 after 0 equals 0. And from here, I move 1 over to the other side. And then I divide it by negative t. And now what do I do to get t by itself?
So you just solve like 2 minus 1 and you get a minus t
What do I get on the left side?
It's just like solve our
And then on the right, you have t by 1/2. Now you know how to get t by itself. Multiply both sides by negative 1, right? Okay.
I think for like the part that's never starting.
Well, of course, that can never be 0, right? Because if I get e to a number, I never get 0.
So like the
So,
the whole thing to be zero.
I think we're on the right track by finding we found the one value of t which can make the derivative 0, right? And we verified it is between 0 and 24. And now we just need to check, is it the global max, or does the global max occur at 0, or does it occur at 24, right?
Like I got t equals negative 11 or 1.
That makes sense.
And the more just now you put it out. Yeah, but then you have to say, you have to put it in negative.
Yeah, so I think you just like natural or not, but then I just divide that by negative 1. So I got.
Oh wow, you guys look like pretty much done. Okay, so let's come back together as a group and see how we can solve this together. So I saw some good stuff out there, and let's just go through it together. So I'm doing my global max theory. So I started with the derivative, and I set it equal to 0. My goal here is, of course, to find the critical points, which are going to be between 0 and 24. So I found the derivative, I factored it, okay, I took out a GCF, and I set it equal to 0. So now what I have is an equation which has the form some number which is not 0 times another number is equal to 0. This tells me that the second number must be 0 because there's no way for the left number to be 0. So this is how I find my equation 2e to the minus t minus 1 equals 0. And to solve this equation, I need to get t out of the exponent, which we were all, I think many of us needed a reminder of how we get t out of exponent. How do we do it? We apply the natural log, right? But first, we're gonna clean this up a little bit. I'm gonna move the 1 over to the other side and divide by 2. I get e to the minus t equals 1/2, and now I apply the natural log. Okay? And now that I've done this, okay, the natural log rule tells us that this is just going to be equal to negative t, and that's equal to ln of 1/2. Okay? And so this t is then going to be equal to negative ln of 1/2, which, if you do it on your calculator, 0.5, apply the natural log, and then make it negative, we get 0.693. Okay, so this is the only value of t which can make the derivative 0. So it is the only critical point. And we double check that this critical point is in fact between 0 and 24. So now what do? I found the critical I found the critical point. What comes next in the global max theory?
Make a table.
We make a table. Very good. So I make a table, and I'm going to put in some t values. How about 0.693 and also 24? Now what do I do with those numbers? Plug them into what?
F of x.
The original function, f of x, right? Or t, or q of t, I guess. Yeah. Okay. And has someone already done this that can tell me what I get? 0 for 0? Is that right? That doesn't sound right. Oh yeah, that is right. Yeah, 0 for 0. Then 9.2. And then, are we getting something different? Okay, let's practice. What do we get when we plug in 0.693? I need to do 20 times e to the negative 0.693, and I subtract from that e to the negative 2 times 0.693. So let's do it. 2 times 0.693. Make it negative. Take e to the x. I'm getting 20 times something minus 0.25. Okay, and the first one, 0.693, I do e to the x, I'm getting 2. So I do 20 times 1.75. Okay, 1.75 times 20, and I get 35. Is that what we're getting? Or did I do a mistake now? Oh, I should have gotten 0.5 here. Sorry. I did a mistake. Okay. So it shouldn't have been 1.75. It should have been 0.25. So if I multiply 20 times a quarter, if I'm not mistaken, I get 5. Is that more like it? Okay. Sorry, I made a mistake there. So we get 5 when we plug that in. And how about 24?
Really small number.
Okay, really small. Really small positive number. Okay. So, what do we think? Where do we have our global maximum? 0.693 is a global max. Okay, how are we feeling about this problem? Okay. So. I think this problem is a little tricky in the same way that the problem was tricky on the exam, right? Problem 5 had an e in it, and we had to do something similar to this where we factor this guy out, right? So anytime we have those, we got to be mindful of GCFs that we can take out of functions. When we set an equation equal to 0, the very first thing in my mind is we need to take a GCF out. And then, if we can, we should factor. Okay? So this is how I would start thinking about these. And yeah, that's pretty much it. Okay, any questions on this one? Yeah.
So what indicator in the problem led you to the notion that you needed to use or to find a global maximum as opposed to like a local maximum?
Okay, so the question was, why am I looking Why am I even trying to find a global maximum as opposed to a local maximum?
Because it's within that day, like within the number of hours in a day that you're trying to find.
Well, the way the question is posed, we're supposed to find the maximum quantity of the drug in the bloodstream. Now, let's say I had a drug which had some kind of, slow release mechanism, right? And maybe some of the drug spills out and a certain amount goes into our bloodstream, but then the rest of it comes in slowly and then has another peak. And I ask you, what is the maximum amount of drug in the bloodstream? If you look for a local max, you might get this maximum, right? Which could be a false global maximum, right? It's a local maximum, but it's not the global maximum, right? So it's a question of uniqueness. So this is why, in terms of the question, it's cueing me to search for a global maximum, because it's asking me for the maximum quantity. Okay, when I see the maximum, then I know either it's a local max and it's only one, or I'm more likely I'm looking for a global maximum. Good question. Any other questions? Okay, then let's move on to section 4.4. Oh, sorry, you can stay in group mode because we're gonna do group in a minute. Or, well, okay, you don't have to stay in group mode. You can go in and out if you want, but we are gonna have a little more group work. Okay, so section 4.4 is all about the applications of this global min-max search to business, right? So there's all sorts of business applications where I might have a function that I want to minimize or maximize, right? Typically I want to maximize my profit, I want to minimize my costs, or yeah, that's pretty much it. Or I want to maybe maximize engagement among my consumers or something like that. Okay, so let's just start by reviewing something really quickly about marginal cost and marginal revenue. Now remember, marginal cost is just a fancy way of saying derivative of the cost function, okay? And marginal revenue is a fancy way of saying the derivative of the revenue function. So if I say something like marginal cost at 500 units, the translation is I'm talking about C prime of 500, okay? That's the translation. Okay, so we have a picture here of a cost function and a revenue function. So the cost function comes up like this. Oh, that's the revenue function, sorry. The revenue function comes up like this, and then the cost function is seen below. And we are asked to estimate the maximum profit. Well, when am I going to have a profit in this picture? It's going to be either region 1 or region 2. What do we think? Hearing some ones and some twos. Who wants to give a justification on their answer? Okay, I'm hearing more twos now. Who can tell me why we're going to have a profit in region 2 but not in region 1? Alyssa?
In region 1, the cost is higher than the revenue, but in region 2, the revenue is higher than the cost.
Exactly. In region 1, the cost is bigger than the revenue. That means we are losing money. In region 2, the revenue is bigger than the cost. That means we are earning money. Now, if I want to maximize the profit, okay, of these 3 lines, which ones do we think is going to maximize the profit? The second one, right? Why? Because the revenue is much bigger than the cost, right? So we want to maximize the difference between the revenue and the cost, which is visualized as the distance between these two curves, right? So the maximum profit if that's 140, I think that Q equals 140 is going to maximize our profit, right? Okay. So, part B. Certainly R of Q is greater than C of Q at that value. Okay, that's true. So how do the marginal revenue and the marginal cost compare at that same value of Q? Let's take a look. Well, if I take a look at my marginal revenue at 140 units, R prime of 140, I'm sorry, this is C. C prime of 140 is going to be whatever the slope of this curve is, right? This line. And of course, R prime of 140 is going to be the slope of this line. Now what do we notice about these two lines? Do they share a relationship? What is their relationship? They have the same derivative, which means that these two lines are parallel, right? So what we recognize is, in fact, I'm noticing that R prime of 140 is actually equal to C prime of 140. Okay, and that actually makes a whole lot of sense because I know that the derivative of the profit function is going to be equal to the derivative of the revenue function minus the derivative of the cost function, which in view of these two things being equal is 0. So I have a profit function whose derivative is reaching 0. That's a good clue that I might be reaching a maximum or a minimum of the profit function. Okay? So in terms of this, I think critical points of the profit function are going to be good places to look for maximums of the profit function, which we always want to maximize the profit function. We want more dollars, right? We're capitalists here. Well, I shouldn't say we're capitalists. I should say we live in a capitalist country. I don't know if you're a capitalist. Okay, so let's work on problem 2 in a group, okay? We just have a profit function here, and we want to find the quantity which maximizes the profit. Okay? So it's another global max search, and we might want to think for a second here about what is the minimum and the maximum quantity of this substance which we might want to produce and sell. That might be a good starting place for thinking. Okay, so I'll be walking around again. If you have more questions, just raise your hand. And I'll be by here.
Why wouldn't we take the
So it is and then I guess you do simply do it over first, because that's like, I guess sort of base closer, so it's not.
Well, when are we going to have
So.
the profit of negative 17,000? I'm going to have a profit of negative $17,000 when I plug in what is, what's 0 units? That means I produce Q unit, 0 units, right? So instead of making it more accurate to me to say that $17,000 is our fixed cost. That's what it costs just for me to own the business, let alone produce units to sell, right?
It's maximizing
So
profit.
presumably, we're going to produce more units up to a point where we're going to then quadratic with a negative term on the square term, right? Negative coefficient on the square term.
The 600.
So we're looking for that.
Right, it's because.
Because like I assume pi of q is always r. Revenue minus cost, and if you're just trying to find so.
But I guess
They both are both on
Right, so we found a critical point, right? So we're looking for the maximum. So do we know whether this critical point is a max or a min?
Like in the table,
First derivative test, or even if we're doing a global search, right? We could also use the endpoints. But if you want to use the endpoints, you gotta find. But yeah, the first derivative test or even second derivative test, right? Because if I have a quadratic function like this, and it's got a negative number attached to the square term, is it gonna look like this, or is it gonna look like this? It's gonna look like this, right? So if I find this critical point, right, probably gonna be the vertex of that.
Did you take
right?
the derivative? I took the derivative.
So it's just a matter of making some kind of argument as to why that's maximum for there, right?
Then would we
Yeah, go ahead.
would we plug that back into just r of q? So that should be the 600 here.
Well, what we're supposed to do is find the quantity which maximizes the profit, right? So we found a value q, which is a critical point of this function. So now you just need to verify, okay, is 75 units the amount of units that I need to make in order to maximize the profit? Or is that gonna minimize my profit? Because that's a pretty big difference, right?
So it's zero
Okay.
via the global revenue.
Perfect.
Wait, so
Yeah.
are sure that's like that?
Well, if I find the zeros of this function, right, then if I plug it in, I'm gonna get a profit of 0, right? So, one thing that we can always think about too is what is the shape of this problem? If I'm going to draw it, it's a quadratic function with a negative on the square term, right? So it's gonna look like downward parabola, right? So if I find the critical point, it's probably gonna be R. But you should make some kind of formal argument as to why it's the maximum, right?
There's a negative in front of the square term. So that kind of makes it a quadratic. Really point the maximum or not the maximum.
Okay, let's come back together. I know you might not all be finished yet. That's okay. We're just gonna come back and solve this one together really quickly. Okay, so I saw a lot of good stuff out there. What people were thinking was, okay, we good? What people were thinking was, well, we want to find the maximum. So let's find first, why don't we just try to find the critical points of this function? Okay, so one thing you could do is try to find the derivative of this thing. Well, pi prime of q is going to be 600 minus 8q. And I set that equal to 0 to find the critical points. And I think that gives me q equals 75, right? Okay, so this is a critical point of this function. And now I need to check, well, okay, is it the maximum profit, or is this a critical point which is going to give me the minimum profit? Right? And there's a couple ways we could do that. We could do it using the first derivative test, right? We could put 75 here, and then we could check a point maybe to the right like 80 and to the left like 70, and verify that our function's going up and then going down, right? That would be one way to check that it's the maximum. Okay. Another way to do it would be the following. You could make a more geometric argument. This is a quadratic function. Quadratic functions with a value less than 0, right? A being -4 in this case is our a value. So the coefficient on the q squared term is negative. Quadratic functions with a negative square term are parabolas who open down, has this shape. Such a function, one could argue, has only one critical point. And that critical point must be a maximum because it's a quadratic function which opens down. Okay, so two different ways in which you could argue that this is a maximum. The second one is a little bit more robust because if you use the first method, then technically we should also check the boundary points, right? And to interpret what are the boundary points of this, I would probably choose the points at which our profit is going to be 0, because before that our profit's going to be negative, after that our profit's going to be negative again, right? So you could just solve for the zeros of this quadratic by using, say, the quadratic formula or factoring or whatever choice you want to use, and then you could make a table and check. I'd put one root here, and then I'd put my critical point, and I'd put the other root down here, and I'd plug them into the function and see what I get, and look for the biggest number or the smallest number. That would be another way to do it. So lots of ways, lots of different ways that we could skin a cat. Not that we would ever do something like that. Okay, are there questions on problem number 2? Okay, problem number 2 is really just a straight application of the global min-max theory to profit, right? That's the only difference is instead of maximizing f of x, we're maximizing pi of q. So, okay, big whoop, I changed the letters. But that's the only difference, right? Okay, not to say that this problem is easy. It does take a certain amount of thinking, right? But what I want everyone to be able to notice is that this is no different than the global max and mins, which we were finding in the last section. So once again, any questions on this problem number 2 here? Okay, I want to spend the last 15 minutes of class going over a different topic, which is still in this section. And this topic is called optimization. Okay, so we're going to see 2 optimization problems. I think we probably won't have time to do group work on the second one like I wanted to. But we'll see some optimization here. Okay, so let me just really quickly, before I go through the algorithm of how to do an optimization problem, let me just show you what one looks like. Okay, so these questions tend to have the following form. We have, okay, for this one, at a price of $8 per ticket, a musical theater group can fill up every seat in the theater, which has a capacity of 1,500. For every additional dollar charged, the number of people buying tickets decreases by 75. What ticket price maximizes revenue? Okay, so in this case, we are going to have to find an equation which takes price as an input and gives us revenue as an output, okay? So our function needs to be a function which takes price as an input, okay? But we only know that we are typically given revenue in terms of the quantity sold, right? So we're gonna have to do a little bit of work here to find an equation of R in terms of R of P, and then we are going to have to maximize that revenue, okay? Similar problem. We have a landscape architect who plans to enclose a region which is 3,000 square feet, okay? And some of the shrubs cost $45 per foot, and some of the shrubs cost $20 per foot along the fourth side. And we're supposed to find the minimum cost. So what do we need to do? We need to find cost, okay, as a function of length and width, right? And then what we're going to need to do is to reduce that equation to an equation of one variable. Okay, so always with optimization, we start with an equation of a function in 2 variables, and we use some extra information from the problem to reduce it to an equation of 1 variable. Okay, so we're going to see how that works in just a second. But let me run through the algorithm. So the first thing we want to do is get an equation, a function, for what we want to minimize or maximize. And usually this is going to first be given in two variables. Okay, so we'll have like an x and a y, or a p and a q, or something like that as our variables. Okay, so maybe we want to minimize the perimeter of a rectangle. So for example, our perimeter could be equal to 2L plus 2W. So two variables here, right? 2 times the length of the one side plus 2 times the length of the other side. That's the perimeter of a rectangle. And then what we want to do is use some outside information to eliminate one of these two variables. Okay, so first, I also know that, say that we want to find this perimeter of this rectangle subject to the constraint. Okay, when you see the word subject to the constraint, you're about to get your extra outside info, right? And then we want to use this to solve for one of the two variables and replace in our previous equation. Okay, so once we do that, for our example, right, we would then get P is equal to, okay, L is 20 over W, so I just replace it. 2 times 20 over W plus 2W. Now I have an equation in one variable, and I need to find the maximum or the minimum of that function based on what the question is asking. Okay, so this is the algorithm. I think it'll become a lot more clear once we see a couple examples. But are there any questions initially on this process? Yeah.
So is this like a systems of equations type of problem?
It is somewhat like a systems of equations problem. The only difference is when you have seen systems of equations before, they are linear systems of equations. So you see things like, 2w plus 2l equals 3, and then you see like w minus l equals 4, or something like that, right? So, but this is a linear system, whereas our system, we've got L times W equals 20. So that's not a linear process. That's a multiplicative process. So we're not just adding certain numbers of certain things to each other. It's a little bit more nuanced than a linear system, but that is the general idea, is to use this substitution process. Any other questions? That's a good question there. Okay, let's see this in action. Okay, so we have a price of $8 per ticket. So I'm just gonna write down some things. I know P equals 8, okay? At a price of $8 per ticket, then my revenue is going to be, well, revenue is always the price of the thing which we are selling times the number that we sell, right? So revenue is always equal to the price of the thing we are selling times the quantity of that thing which we sell, right? That's gonna give me the amount of money which comes in. And now I need to reduce this, okay? I need to reduce R equals P times Q to a function of only P, which means I need to use some outside information in this problem to get Q in terms of P. In other words, if I have the price of the ticket, how do I know how many people are gonna come to my musical theater group? So I need Q of P. Now, what do I know from the problem? I know that if I charge $8, then the capacity will be 1,500. Okay? The capacity is going to be 1,500 if I charge $8. Then, for every additional charge, for every additional dollar charge, the number of people is going to decrease by 75. Is there anyone who can tell me a function which is going to represent that relationship? Well, let's ask ourselves, what kind of function is Q of P going to be? It's a certain amount when we have 1,500, and then for each additional dollar charged, the number of people decreases by a fixed amount. What kind of relationship? Sorry, I heard it.
Linear.
Linear, right? This is a linear function. You agree that Q of P is a linear function. So let's just say it's a function like MP plus B. What is my goal now? I need to know what are the numbers M and B. Okay, I need to know what the numbers M and B are. Well, I think I can immediately find out what M is. M is going to be, how does this function change as we increase P? Well, for every P we increase, the dollars goes down by 75. So M is going to be what? Negative 75. So Q of P is equal to negative 75P plus B. How do I get B?
The originals, the $8.
Yeah, if I have $8 per ticket, then the quantity sold is 1,500. So I plug those in. 1,500 will be equal to negative 75 times 8 plus B. Okay, now I just need to solve. So 75 times 8, okay, 600. So I add it to the other side. 2,100 is equal to B. So now I know what Q of B is. This all tells me that Q of P is equal to negative 75P plus 2,100. Okay. So now I've got Q in terms of P. So the goal at this stage is, of course, to write the revenue function, which is what I want to maximize, in terms of P. So I did all this work to find Q in terms of P, so what I'm going to do now is replace the Q here by this function of P. So R of P is going to be equal to P times what Q is in terms of P. So I just put negative 75P plus 2,100. Okay, so now I have a function of R in terms of P, and I want to maximize this function, which means I want to find, okay, what ticket price maximizes revenue. I'm looking for a global max here, okay? This is telling me I need to find a global max. Okay, so I have this function, and again, just looking at it, I can tell what kind of function this is, right? If I multiply P times negative 75P, I'm going to get negative 75P squared, which means what type of function is this? Quadratic. And it opens down or up?
Downward.
It opens downwards, right? So that means as long as I find the critical point where the derivative of this guy is equal to 0, that's going to be my maximum, right? All right, so let's go ahead and do that. This is my function, which is the same as negative 75p plus 2100p, and now, P squared, and I take its derivative. So r prime of p is negative 150p plus 2100. Set that equal to 0. I get p equals 2100 over 150, which is 2100 divided by 150, 14. So this is the ticket price for which is going to give me the vertex of this quadratic function. Okay? And I know that since the function is a quadratic function which opens down, I know that the vertex is going to be a maximum. Okay, so I'm confident in saying that $14 maximizes revenue. Okay, now that I've done this, I want to return to my algorithm and show how this algorithm is working. So, first, we get an equation for the function we want to minimize or maximize, and we don't worry about the fact that it may have multiple variables at first. For us, that was our r equals pq. Then, we get an equation for one variable in terms of the other. That was how we did our q equals negative 75p plus 2100. We got an equation for one of those variables. And then, in the equation r equals p times q, like I said in step 3, we take this q and we replace it in the equation from step 1. In doing so, we turn an equation that was in 2 variables into now an equation which is in 1 variable. That was our p times negative 75p plus 2100. So we take an equation in multiple variables, we turn it into an equation with 1 variable. And then we know very well already how to minimize or maximize a function in 1 variable. That has been the entirety of chapter 4 up until this point. Okay, so that's why the last step is apply global min-max theory. Okay, once we get to step 3, we start at the beginning of the steps for finding global mins and maxes from the previous section, i.e. find the critical points, make a table with all the critical points and the boundary points, look for the biggest number. Okay, any questions on this optimization stuff? All right, if not, then we'll close there for today. Thanks for your attention, and thanks for your cooperation and group work. Have a good weekend. And if you have any questions, then I have office hours today from 3 to 4:30. Hey.
I actually have a question.
Yeah. So hang on, let me stop the recording.